All right, so far we have seen how binary numbers are represented in base 2, and we know how to convert the numbers from different bases. And we also know how to do some arithmetic operations. Now, we are going to move to a new section, which is related with the complements. Now, this section is all about, again, with the arithmetic operations. Complements are part of the arithmetic operations, and this is how the computer or a microcontroller or any digital system behaves. Now, what is complement? Now, when we talk about complement, it's like, as we already mentioned, maybe in the complementary way, it's like the opposite of it. Now, with the complements, we are actually achieving some arithmetic operations in more simpler way. What do we mean by that? Now, and how do we use this is all related with the binary arithmetic. So before I get into the complements, let's talk about how can we represent a negative number in binary. So how do we represent negative numbers in binary? That's a question that we need to ask now. So one thing that we can do is called sign magnitude. Now, what is sign magnitude? So let's say I have got 5, and this 5 can be represented as either -5 or +5. Okay, this is decimal. Now, when we consider binary numbers, that 5 is 101 in binary. Now, if you want to represent it with -5, that's 101, we just add 1 in front of it. And if you want to represent it as +5, 101, we just add 0 in front of it. So actually, 1 represents the negative sign, and 0 represents the positive sign. So this is called sign magnitude. So for example, if we do another one, let's say 8. Now 8 is 1000. Now if we want to represent it as -8, that becomes 1 and then 1000. And if we want to represent +8, that becomes 0 and then 1000. This is called sign magnitude. We just represent the sign bit with a binary number. This is one way of representing negative numbers. We also have two other ways which are related with the complements, r-1s or 1's complement, or r's complement, which is known as 2's complement. So normally, as we already said, we use negative symbol on a paper, and absence of it implies positive. Or you can just put a plus sign in front of it. And as I already mentioned, in digital system, computer use sign magnitudes as negative sign for 1 and positive sign for 0. And I can give you a couple of examples, like 85 plus 85. As you can see, we put 0 in front of it because 101, 0101 is 85. And if you put 0, it becomes plus. 11111 is 127. If you put 0, it becomes plus 127. If you put minus in front of it, that becomes minus 85. But this is only valid in sign magnitude system. Be careful, because next we are going to see how these are done in complements, and they are differ. Okay. So when we deal with the signs, like we are dealing with the ordinary decimal arithmetic, we have got the similar rules. So for example, addition of two numbers in the sign magnitude system. If the signs are the same, we add two magnitudes and give the sum the common sign. And if the signs are different, we subtract the smaller magnitude from the larger one and they give the different sign of the larger magnitude. Okay, so this is actually using the same approach as we do it with decimal arithmetic. Now, when we talk about arithmetic addition, we are actually adding two numbers together as we have seen in the previous section. Now, addition is simple. We can easily do it. But when it comes to the subtraction, in digital system, it has a higher cost because you need to have a subtract operations using a subtractor, which requires an extra hardware, which will cost more. You have to think about the area, the power dissipation, and so on. Now, in arithmetic addition, when you add two signed binary numbers with negative numbers represented in sign two's complement form, which we are going to see later, it's actually obtained from the addition of two numbers, including their sign bits. And the carryout of the sign bit is discarded. Now, we can do an example about that. Let's say I have got plus 6 and plus 13. Now, what is plus 6? Plus 6 is normally 110. If you want to make it plus 6, you just add another 0. You can have it this complete 8 bits or 7 bits or 10 bits or 16 bits. I'm just using 3 bits to represent the number and the sign bit, and it becomes 4 bits. Now, when you think about 13, 13 is going to be 1101. Now, in order to accommodate enough digits, let's get rid of the sign bit first. Now, this is 3 bits, this is 4 bits. Now, first, before we do anything else, we have to make plus 6 as 4 bits as well. So I just add extra 0 in front of it. I just want to accommodate enough digits so that I can do some operations with it. Now, as this is plus and this is plus, I'm just going to add the sign bits in front of it. Now I have equal number of bits and I can easily do the calculation, which is going to be addition, and I will end up with plus 19. So that means 1 plus 0 will be 1, 1 plus 0 will be 1, 1 plus 1 is 2, we have got 0 and the carry 1, so again 2, 0 and the carry 1, and we have got 1. And that represents 19 in binary. It's actually plus 19. Okay, so again, we can use the sign bit over there, and that will represent plus 19. How about if we do it this way? Let's say we have got minus 6 and plus 13. Now again, 6 is 110, which I'm going to show next. We can take the 2's complement of 6, okay? So that becomes 0, 1, 0, okay? I'm going to show you the method later. That's 2's complement. So then I also think about the sign bit. So that becomes plus 6. Now that becomes, as a sign bit, it's going to be 1. Okay? I'll explain these in details. I'm just showing them as an example for now. And plus 13 is, we know that is 1, 1, 0, 1, right? So again, we have to accommodate enough digits. We have to make that 4 as well, and then add the sign bits on both sides. So that becomes 1, and then we have got the sign bit. Okay, and similar applies to the 13. So 1, 0, 1, 1, and we have got the sign as 0. Okay, so then what we need to do is we just need to perform the addition of this part, which is going to be 1, 1, 1, 1, 1, 0, carry 1, 0, and then we have got another carry. And this is going to be discarded, and we end up with 7, which is the value of it. Now, how is that going to be done? And why are we doing this? Now, the first thing to do, instead of doing a ordinary subtraction like we have done it before, we are going to use complements. Complements are going to help us in a way this we will have reduced area, low power consumption, and reduced cost. And how is that going to be done? Rather than using subtractor, we are going to use an adder. Like we use in addition, we are going to use an adder. An extra circuitry that we will need is just an inverter. Okay, and this is how we are going to do the complements. All right, so again, the same rules. So these are just the examples. The same rule applies. So in 2's complement form, we take the 2's complement of the subtrahend, including the sign bit, and add it to the miniant, including the sign bit. I will explain the details in the next slides. Now, carry out of the sign bit position is discarded, and the operations plus or minus A minus plus B is going to be plus or minus A plus minus B, as usual. And plus or minus A minus minus B is going to be plus or minus A plus plus B. The same rule applies in ordinary mathematics, so we are not changing anything. Okay, so let's get into the complements now. As we know the details and the rules about arithmetic operations for the addition and subtraction, let's talk about the complements now. So once again, complements are used in digital computer to simplify the subtract operation and for logical manipulation. So simplifying operation lets simpler, less expensive circuits to implement the operation. As I already mentioned, we are just using adder circuitry and an inverter. And we have got 2 types of complements, the diminished radix one, which is R minus 1's complement, or the radix complement, which is R's complement. So let's start with the diminished radix, which is R minus 1's complement. Now, what is R minus 1's complement? We have got a special formula for this, where we have got R minus 1 minus R to the power n minus 1 minus capital N. Now, this small n is actually representing the number of digits. And R is our base 10, base 2, and n is our number that is given. Okay? Now, let's try with this decimal first, and then we will try it with the binary numbers as well. So let's say we have got a number 54 in decimal. So if we use this formula, n is 2, r is 10, and n is 54. Now, if we put everything into a formula, it's going to be 10 to the power 2 minus 1 minus 54. Now, 10 to the power 2 is 100 minus 1 minus 54. Now, what is important over here? That becomes 99. Then minus 54. Now, this is called diminished radix, or if you are using a base 10, we call it 9's complement. Why do we call it 9's complement? Because whatever the number over here, 10 to the power 2, 10 to the power 3, 10 to the power 4, minus 1 is always going to give you something with 9. 9, 3 nines, 4 nines, 5 nines, whatever it is. That's why it's called 9's complement. Okay? And when you do the subtract operation, That becomes 9 minus 4 is 5, and 9 minus 5 is 4. So we are going to get 45 as the 9th complement of 54. Then we can do the arithmetic operation after we do the complement. I'll show you the rules for that as well later on. But let's first understand diminished radix. Now this is in base 10, and we can actually repeat the same thing with base 2. Let's say again we have got 101, which is equivalent to 5 in base 2. So if I want to take the diminished radix of this, again r to the power n minus 1 minus n is the formula. So r is 2, n is 3, and the number itself is 101. So we can easily put everything into a formula. That means 2 to the power 3 minus 1 minus 101. Now what is 2 to the power 3? It's 8. So how do we write 8? In binary, it's 1000, then minus 1, and minus 101. So 100 minus 1, it's going to give you 111. So 8 minus 1, it's 7. So as you're always going to get 111, triple ones, 4 ones, 5 ones, whatever this power is, this is called ones complement in base 2. Okay? We always called it ones complement. We don't really call it diminished radix, we call it ones complement. All right, so we have got 111 minus 101, so 7 minus 5, that's going to be 1 minus 1, 0, 1 minus 0 is 1, 1 minus 1 is 0, so we have got 2. So that means the ones complement of 5 in base 2, it's going to be 2. We can try another number. Let's say we have got 1010, which is equivalent to 10. So 1010, R is 2, N is 4, and capital N is 1010. So R to the power N minus 1 minus N. So R is 2 to the power 4 minus 1 minus 1010. To the power 4 is 10000. Minus 1 minus 1010. And this is going to be 1111. Because 2 to the power 4 is 16. 16 minus 1 is 15. Again, ones complement minus 1010. So 15 minus 1, 10. That it's going to be 1 minus 0, 1. 1 minus 1 is 0. 101. And that will be 0. So the 10th complement, 2's complement of 1010 is 0101. Now, this is the way of doing using a formula, but there is also a shortcut version of this where you don't need to use a formula. That's the tricky one. Now, what is it? I'll just rewrite the first number, which was 5 in base 2. Now, the short way of doing this, in ones complement, diminished radix, we just need to invert each of these bits. So 1 becomes 0, 0 becomes 1, and 1 becomes 0. So as you can see, we have got the same answer. Let's try 1010. So 1010. Invert each of these bits. 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0. So it's exactly the same thing. You don't need to use formula. Whenever you see a binary number, you just invert each of these bits and you will get ones complement. straightforward. Let's try another one. Let's say we have got a number 1, 1, 0, 1, 0, 1 in base 2. Then if we invert each of these bits, that becomes 0, that becomes 1, 0, 1, 0, and then 1. And that's, sorry, that should be 0 as well. Okay, so we inverted each of these bits and we got the ones complement. That's it. Okay, if we go from the slides as well. So decimal numbers, base 10, as I already mentioned, it becomes 9's complement. So r minus 1 is always going to give you something with 9. And then we subtract the number from 999 and we get the 9's complement. And for base 2, it's 1's complement because r minus 1, it's always going to give us 1. Okay? And here's the first example, which is 0011. Now, 4 digits to the power 4 minus 1 minus 0011. Then 16 minus 1, that becomes 1000. And then minus 1, it becomes 1111, which is 15. And 15 minus this number, 1111, minus 0011, and that becomes, as you can see, 1100. And if you want to directly use the ones complement, invert first bit, 1 becomes 0. Invert second bit, 1 becomes 0. Third one, 0 becomes 1. And 0 becomes 1. And ta-ta, we have got 1100. And that's how we do the ones complement. So as we are subtracting binary digits from 1, we can either have a 1 minus 0 as 1 or 1 minus 1 as 0. So which actually changes bits from 0 to 1 or 1 to 0. So from here, you can easily see that ones complement is just changing each of these bits, ones to zeros and zeros to 1. So that's how we do the ones complement. Okay, so diminished radix or ones complement, all zeros becomes 1 if we summarize it, and all ones become 0. And if you add the number and its ones complement, you are always going to get a result as 1. Okay, so the original number and the ones complement, which is the inverted one, when you add them together, it will always going to give you 1. Okay, so this is diminished radix. Next, we are going to see radix. Now, radix is similar to diminished radix. We call it tens complement in base 10 or 2's complement in base 2. So the previous one was 1's complement and 9's complement. Now this is 10's complement and 2's complement. So it's, as you can see, it's just the 9's complement plus 1 or 1's complement plus 1. So this is what we are doing in this. So this actually becomes the radix complement as an equation wise. It's r to the power n. We don't have minus 1 anymore, which we have done it over here. We just have minus n. So the new formula is r to the power n minus n. Because we want to add 1, then minus 1 plus 1, they just get rid of each other. And the new formula is r to the power n minus n. So again, we have got two options over here. Let's start with base 10 for the tens complement. We can use the formula. So the example that we have got over here, it was 54. So let's find the tens complement of 54. So 54 in base 10, and we want to find the tens complement. So R is, again, 10, N is 2, and n is 54. So r to the power n is just going to be 100, or let's write the formula. So 10 to the power 2 minus 54. So that becomes 100 minus 54. Okay, so now 100 minus 54, it becomes 46. So in the previous one, this is actually the tens complement. In the previous one, if you do remember, we have got 45. Now we have got 46. So it's just added 1 to it. So 9's complement plus 1 will give us 10's complement. If 9's complement is easier for you. This is one way of doing this. There's another method as well, which is, I believe it's a shortcut version. Let's say you have got 54. Now, what we can do is, the first non-zero is going to be subtracted from 10, and the rest will be subtracted from 9. This is the rule. It's always the case. So that becomes 6, 10 minus 46, 9 minus 5 is 46. That's it. You don't need to use formula. Let's try another one. Let's say we have got 1240. Now in this one, the first zero remains as it is. So we plot 0. The first non-zero one, it's going to be 10, and the rest are just coming as 9. So when we do the subtraction, that becomes 0, 10 minus 4, 6, 9 minus 2, 7, and 8. And this is the tens complement of 1240. Okay, this is base 10. Now let's see base 2. So the first number was 101. In base 2, we have got the formula in 2's complement, r to the power n minus n. So r is 2, 3 minus 101. And we have said before, 2 to the power 3 is 8, so 100 minus 101. And that becomes 011, which is the 2's complement of this number. Again, this is using the formula. If you don't want to use the formula, the shortcut version of this, 101, the first one remains as it is, and the rest will be inverted. So 0 becomes 1, and 1 becomes 0. Again, we have got the same answer, and this is also 2's complement. Okay? So 101, the 2's complement is 011. Let's try another one. Let's say we have got 1101, 0, and 2 zeros. Again, zeros remain as they are. Then 1, the first one always remains as it is, and the rest will be inverted. So 0 becomes 1, 1 becomes 0, and 0. So this is the 2's complement of this number. So this is always the case. Okay, so the first least significant bits, if they are 0, they remain as they are. The first one is going to remain as it is, and the rest will be inverted. So this is called radix complement, or 2's complement in base 2, or 10's complement in base 10. So the rules: by leaving all significant zeros unchanged in 10's complement, and by subtracting first non-zero least significant digit by 10 and the rest from 9, and the 2's complement form, by leaving all significant zeros and the first one unchanged, like we have done it over here, and then replace ones with zeros and zeros with ones and other significant digits. So this is just showing the example, or what you can do is take the 9's complement and add 1. That's also possible. Or takes the 1's complement and add 1. That's also possible. So for example, 1, 0, 1 again, 1's complement of this 0, 1, 0, right? We just inverted each of these bits. And if you add 1, that becomes 1, 1, 0. So that becomes 2's complement. So here it is 1's complement. And from here to there, it's 2's complement. You can use it this way as well. There's nothing different. So take 1's complement and then add 1. So just invert each of these bits and add 1. You get 2's complement, or leave all the zeros as they are, leave the first one as it is, and invert the rest one. So 1 becomes 0, 0 becomes 1, and 1 becomes 0, and that's it. So the complement of the complement restores to its original value. So r to the power n minus r to the power n minus n, it's actually going to give you n. So based on the knowledge that we have gained now, we can derive this table for representation of signed numbers using 4 digits. So decimal numbers 0 to 8, binary numbers 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. You'll get used to a counting of these. And then 8 is not represented, and in negative, so that becomes 0 minus 0. If you are just using sign magnitude, you just need to add the sign bit, which is 1 in front of it, as you can see. And if you are using 1's complement, you just need to invert each of these bits. So 0, 0, 0 becomes 1, 1, 1, 1 becomes 0, 0, 0 becomes 1, 1, 1, and so on and so forth. Just inverting all of those bits. And the 2's complement, so it's not valid for 0, then 1 stays same, the rest will be inverted. 0 stays same, 1 stays same, the rest will be inverted, and so on and so forth. And this is the table that we can derive it. Now, let's see how are we going to use these complements and why are they so important. As I mentioned, it reduces the hardware cost and so on. But there are some rules over here. So the subtraction of two n-digit unsigned numbers, m minus n in base r, can be done as follows. So what do we need to do? Add the miniant m to the r's complement of subtrahend n. So we have to take the complement of minus n so that it becomes something that we can use it as a addition rather than using a subtract operation. So we take the complement of n and then add to the m. And two important things, if m is greater than n, the sum will produce an n carry in the end, which can be discarded. So what is left is the result. Or if m is less than n, it's not going to produce any n carry. So what we are getting is actually the complement number, which represents a negative number. And in order to make sure that you got the right answer, so take the r's complement of the sum and place negative sign in front of it. Now, generally, computer uses 2's complement. And all the arithmetic operations related with subtraction, they're all performing the 2's complement. 1's complement is just the intermediate state to show it. But generally, computer uses 2's complement. Okay, so let's see the example how we are dealing with these complements now. So we have got two numbers, x and y. And we have to do some operations, x minus y and y minus x. So let's write down x first, which is 1, 0, 1 and 0, 1, 0, 0. And y is 1, 0, 0. We have got 4 zeros and then 1, 1. So two numbers, equal number of digits. Okay, so 3, 5, 7 digits. Now A is saying we have to do x minus y, and B is saying we have to do y minus x. So let's start with x minus y. Now we know that as this is x minus y, we have to take the complement of y. So step one, 2's complement of y. So let's write down y, 1, 4 zeros, and then 1, 1. Now the 2's complement of that, the first one remains as it is, and the rest will be inverted. So 0, 1, 1, 1, 1, 0. This is the 2's complement of y. Then step 2, add 2's comp of y to x. Okay, then, if we want to do that, that means we have to write x first, 1, 0, 1, 0, 1, 0, 0. And then we have to write the complement of y, which is 1, 0, 1, 1, 1, 1, 0. And then we put a plus sign, so no more minus sign over there. Then 1, 0, 1 plus 1, 0, carry 1, 0, carry 1, 3 ones, then another 1, 0, another 1, and 0, and then another 1. Now the question is m greater than n? Is x is greater than y in this case? So if we start from the higher digits, 1, 1, 0, 0, and this is 1 again, and this is 0. So that means this one is a bigger number than this one. So x is greater than y. In this case, we discard the carry. Okay, so we discard the carry, and the value that we get is going to be our number. If you want, we can check what's the output of that is. So let's write this down. So what is x and what is y if you want to convert it? So 0, 1, 2, 3, 4, 5, 6. Let's consider it that way. So 2 to the power 6 is 64 plus 16 is going to be 80. So 64, 16, 80, and 2 to the power 2 is 4. It becomes 84. Now this one, 64, again 64 plus 2 plus 1, it's going to be 68, right? So 67. So 84 and 67. So what do we expect here when we do 84 minus 67? Then 0, 1, 2, 3, 4. 2 to the power 4, 16. And then plus 1, it's going to be 17. So 84 minus 67 is actually going to give us 17. So we got the right answer. Then let's try B, which is y minus x. Now we have to take the complement of x. So let's write down x first. So x is 1, 0, 1, 0, 1, 0, 0. Then the 2's complement of x. So we keep the first zeros and the first one as it is, and we invert the rest. So 1, 0, 1, 0. So this is the 2's complement. This is 2's complement. Now, as we have got the 2's complement, we just need to add it to y. So what is y? Now, y is 1, 0, 0, 0, 0, 1, 1, and the complement of x is 0, 0, 1, 1, 0, 1, 0. And when we add them together, this becomes 1, 1, 1, 1, 0, 1, 1. So what do we expect? 67 minus 84, it's going to be minus 17, right? So we are expecting minus 17 here. Is this minus 17? Now, as m is less than n in this case, that means this is in the 2's complement form. So if I convert it back by keeping the first one as it is, inverting the rest, this should give us 17. This is 16. This is 1. So 16 plus 1 is 17. But we have to put the negative sign in front of it to represent it as minus 17. So this is how we are using the complements. And as you can see, we are not using in subtract operation. We are just inverting and adding. So we perform invert operation and we perform add operations, nothing else. So these are just repeating the steps that I have done over here. So x minus y using 2's complement, take the 2's complement of y, like we have done it, as you can see, and then add 2's complement y to x, that becomes 1, 0, 0, 1, 0, 0, 1. Discard the n carry as m is greater than n. So we discard the n carry and we got 17. Then that becomes 1, 0, 0, 1, as we have found over here. And the second one is y minus x, so that means we have to take the x to its complement. So keeping the first zeros and the first one and inverting the rest, 0 becomes 1, 1 becomes 0, 1, and 1, 0. So then we add the complement of x to y, and we have got 1, 1, 0, 1, 1, 1. So as you can see, there is no n carry. We just need to invert. We just need to take the complement and put a negative sign in front of it, and that becomes minus 17. Okay, so in these type of operations, you might get some overflows. So what is overflow? Now, if you are dealing with a physical hardware in digital design, where we have to store these numbers somewhere, we just use registers. So register, if you are having a 4-bit register, you can just store 4-bit number over there. If you are using a 5-bit register, that means you can just store 5 bits. You cannot store 6 bits into a physical 5-bit register. So that's where the overflow becomes an issue. Okay, so when you do an operation, sometimes you are going to get an overflow because the result is not going to fit into the fixed physical register. And how do we detect overflow? Overflow can be detected based on the last significant carries, the most significant carries. If they're equal, that means there are no overflows. But if they're different, like these ones, you might get an overflow. Okay, so 0 and 1, 11, it's not going to fit. That means there is an overflow. Or 1, 0, minus 11, again, it's going to be an overflow. Okay, so if you don't have enough digits, sorry, if you don't have enough registers to fit all the bits that you have got, that will cause an overflow. And in order to deal with that, we compare two most significant leftmost carries in order to detect an overflow condition. That's all I want to say for this section. We talked about the complements, and rather than using the subtract operation, we just use complements and perform addition operation in order to reduce hardware complexity, reduce the cost, area, and power consumption.